So, thank you. Hello, everyone. Welcome to this talk on building regressors and classifiers in Python. My name is Abhigyan Shrivastava, but I guess you can just call me Abhi because it's too complicated. Okay, so about me, I am a software engineer at Adobe right now, the company that makes Photoshop and PDF readers. And I'm in transition to changing that to Microsoft next month. So I'm a notice period engineer. Uh, we are going to talk about building regressors and classifiers, and we are going to start at the very basics. We're going to talk about some mathematics, and then we will, by the end of the 25 minutes, we will be able to create a model in a regressive model in Python that actually makes real-time predictions. So there's a lot of stuff to discuss. We might not have time for questions in the end, so I will be available to take all the questions after the talk during the break. All right. So beginning with the very fundamental questions of what is machine learning. So in my opinion, when you teach the computer, giving it some sample data, and then the computer is able to make predictions for data that for brand new data, then that is what machine learning is. Machines are dumb by default. But if you teach them and then ask them to do the work for you, that is what machine learning is. So essentially training it technically and then testing it on real-time data. Very quickly on the types of machine learning algorithms that we have right now, it's supervised, unsupervised, and reinforcement learning. And we are going to spend most of our time building the supervised regression model, but just trying to understand what are the different types of models there are. In supervised, we have label data. For example, let's say we are trying to create a model for predicting the house prices, which is the dependent variable, and the independent variables could be the square feet area of the house, the location of the house, number of bedrooms, number of washrooms, is there a basement attached to it? So all these different categories or all these different columns can be used to accurately predict the actual price of the house. So that is a supervised learning algorithm. In unsupervised, when you have unlabeled data, for example, you have like a log file with millions of logs and you want to group them by some type. So you essentially are trying to find a pattern in a lot of unsupervised data. That is unsupervised learning. And the third one is reinforcement learning. So this is where machines learn by trial and error. For example, a robot trying to walk. So what happens, let's say it falls, it penalizes the decision that led to this fall. So the next time, it will have less weight. So just looking at the types of algorithms, the subtypes actually. So for supervised, we have regression and classification. In regression, we have like a continuous data points, and in the end, we want to predict values on the basis of that. But then in classification, it's like yes, no answers. For example, you are given review feedback and you want to analyze if it's a positive review or a negative review. That's a classification problem. So that comes under supervised learning because it is again labeled data. And then unsupervised, we have clustering and dimensional reduction. For example, you have a lot of people coming into your shop. You want to group them by the kind of people who buy items less than 50 pounds, 50 to 100 pounds, like that. Anything related to that is clustering. That's unsupervised again. For example, the log file example that we just took. And then the third one is reinforcement learning. Again, there could be various types depending on how exactly you want to train maybe your robot. It could be value based. It could be, you can set certain policy that this is what you have to do when you actually fall. It could be model. It could be incentive based. So if you successfully walk, you incentivize that series of decisions, and then that's how the model keeps on learning. All right, very quick math just before we actually build our model, because I want to start it from the very basics. So let's say you're given this data. We have the house area and then the price of that house. So we have three examples already given. If the house area is 100, the price comes out to be 50. If the house area is 200, the price comes out to be 100. 300 is 150. Anybody in the room can guess what would be the price if the house area was 500? 250. That's absolutely correct. And how did you do that? Okay, yeah, that is correct. Yeah, that is a sequence. So if you try to extract an equation out of this, this is a linear relationship between the house area and the price. There is a sequence, yes. Apart from that, if you look at the price, it is always half the house area, right? So if y, let's say, was the price and x was the house area, y is always x by 2, right? So this is the equation of a straight line, y equals mx plus c, and here the c, the constant, is 0 and m is 0.5. So y is always x by 2. That's how you were able to get the answer 250. But what happens if the data is a little complicated, something like this? House area and price. It is humanly difficult to, I would not say impossible, there could be a Terence Tao here. It is humanly difficult to find the relationship here just by looking at the data. The previous one was very easy because this here, in this case, let me reveal that it's a polynomial relationship. The y, the price, has a polynomial relationship with the house area. So it looks like 2x squared plus 3x plus 4. So the answer comes out to be 3328. Now, in the first case, when it was very easy to predict, is when humans can easily do the task. But when it gets complicated, that's when we deploy machine learning algorithms to extract this equation from the data, so that later on when you have a new data, you just feed it into the equation and the machine just gives you the response. So that's essentially what is machine learning. You give it a lot of data. In the backend, it builds equation. Later on, you ask it to predict something, and it just feeds it into the equation. That this is as dumb as it sounds. It just feeds it into the equation and solves the equation for you. That is all machine learning regression model is. Why do we use Python? That is because it is extremely easy to read. There are a bunch of pros to Python. First thing, it is extremely easy to read. It is so easy. Sometimes I'm reading the code and I feel like I'm reading literature. You can read it and understand it just at the very instant. You have a lot of support. It's a huge ecosystem of libraries. There is a library for literally anything in Python. We have a literally very strong community, just for example, the one that we are here in. And then it is very widely used in the industry. For example, at Adobe, whatever models I have built for the company, every single one of them was in Python. How do we create a model? This is a very small timeline. So we start with data handling. We'll use the two libraries, NumPy and Pandas, to do that. Then we'll visualize the data. We'll use Matplotlib and Seaborn to do that. We'll train the model using Scikit-learn. We're not using TensorFlow right now because it's deep neural network building library, and we are just going to build a regressor model. And then in the end, we are going to predict the values to check if the model is working perfectly or not. Quickly, steps to building the model. First, we're going to import the data. Then we'll handle the null values. There is a lot of pre-processing that needs to happen before you actually train the model. So we import the data, we handle the null values, we handle the outliers, we handle categorical data, we do some feature scaling, and then finally with all the data, we split it into train set and test set. We use the train set to train the model and the test set to predict values if it is working as expected. All right. Let's go to Google Colab. Let me upload the data real quick. So we are going to run this for anyone who is not aware of what is Google Colab. We can run code here in sequence of whatever sequence we want. So let's say I want to run this block. I'm going to play here, and then the code will stop execution here. So I can move to the next block whenever I want, right? So we'll import the libraries first, and then we'll import our housing data that I just uploaded. What does it look like? We're going to print house.head, and it is going to give us the first 5 lines of the file. And if you look at it, we have a lot of columns here: price, area, number of bedrooms, number of bathrooms, number of stories. Is it on the main road or not? It's a Boolean column, yes or no. Is there a guest room? Yes or no. Is there a basement? Yes or no. So these are all categorical variables. And number of parkings available, that's good. Is it in a preferred area? Yes or no. What is the furnishing status of this house? Now, this one is interesting because we have 3 categories here. It could be furnished, it could be semi-furnished, or it could be unfurnished as well. So let's see how we build a model using all these columns, and in the end, we'll try to predict this price of the house. So we'll get rid of the price from here. We'll train the model on the rest of the data, and we'll try to predict price. Let us look at the shape of the model. Okay, so sorry, shape of the file. So we have 545 rows and 13 columns. Why do we do that at all? Now we know, so it is all about getting a feel of your data first before building the model. You get the feel, what kind of data it is, how many rows are there, what kind of columns are there, are these integers, are these categories. This is what you can use later on to take decisions when you handle all the side tasks which are going to come very soon. So in this case, we have 545 rows. That means we have the leverage to skip some rows later on if we see some problems with a bunch of rows. It's a manual work, right? So what if somebody left one of the columns blank? That entire row becomes useless for us. We have two options at that point of time. We either fill that value with the mean of the rest of the values, the median of the rest of the values, or we just drop it. Here, we have the liberty to drop it because 545 rows versus 544 rows, it's not going to make a lot of difference. Let us look at the info. So this essentially tells us what kind of data types are there. Again, as I said, we're trying to get a feel of the data. So everywhere it says object is a categorical data. So we're going to handle that. Now we'll describe the data just to try to understand if there are any outliers, because we get the minimum value of that column as well as the maximum value of the column. For example, we have minimum 1 bedroom and maximum 6 bedrooms. So, okay, this looks fine. What if there were 50 bedrooms in a house? Somebody could be filthy rich, but that data we cannot use to train the model because that is breaking the usual trend of the kind of model we are trying to build. So, perfect. Let us check for null values. So this is the command you can run to check for null values. What happens, it finds all the columns where there's null and then it finds a percentage of that. So 0.183% of the area values are null. We'll have to handle that. How can we handle that? We either drop that column once and for all, or we just populate that particular column with a median or the mean of the rest of the data, because that will follow the usual trend of the model that you're trying to build, or the pattern that we're trying to find in this data. We can, so in this case, we're not going to drop it, we'll just fill it with the median. So we run this to fill it with the median, and then we'll check again for null values, and you see all the null values are gone. So 0% null columns now. Next, we are going to do some outlier analysis, and to do that, we are going to print a box plot of all these columns. What is a box plot? To be precise, it simply tells you the spread of the data. So this blue box you see here, for example, for price, tells you the space between the first quartile and the third quartile. Quartile is essentially, let's say you have numbers ranging from 1 to 100. Everything that is less than 25% of the data is the first quartile. Everything that is between 25 and 75, it's the second quartile, and beyond 75, it's like the, 25 to 50 is the second quartile, 50 to 75, third quartile. It works like that. So the spread of the data, it's very good to have the data between, within the second quartile and the third quartile, or the first and the third quartile, but we can accept all those data points that are maybe well within the limits of 1.5 times the max, the third quartile, or 1.5 times quartile range of the first quartile before that. So because that data is still following the pattern, anything beyond that, so these whiskers actually tells you how far the 1.5 times the quartile range is it. So this is the quartile range, this is 1.5 times the quartile range, and all these numbers are beyond 1.5 times limit. So we are going to get rid of that. Again, we might have 1-2 data values there, that's fine, but if we have a lot of these, for example, here we have 1, it's fine, but here we have like, I don't know how many are overlapping here. We need to get rid of those because they are breaking the usual pattern of the pricing that we are following. So these houses are very expensive if you look at it. There could be some rich people living there, but we don't want to use that to train the model because they're rich. Or in other words, they are not following the usual pattern of the society, is how I should put it. So we'll do the outlier treatment for price. Everything that is beyond 1.5 times the interquartile range. Interquartile range is the distance between Q3 and Q1. We are going to drop them. This is done. We are going to do that for price. We are going to do that for area. And then we are going to print the box plot again. Okay, this looks a lot better now. 1 or 2 values beyond the quartile range, and that is, so this is, this new graph is as per the new calculations. So you might still see some values beyond the quartile range, but that is fine. 1, 2 values are absolutely fine. All right, now we are going to print the pair plot of this data. Why? Pair plot gives you every column versus every other column. It gives you a graph of that. So why do we do that? Because it skips all the categorical variables, like do you have a basement in your house or not? Yes or no. It's going to skip that. So this is how you can get more feel of the data. First thing. Second, you can realize what are the categorical variables that need to be handled, right? So all these are integers, stories, parking count, everything is fine. But then all the categorical variables were skipped. So now we know what were the categorical variables. These were the categorical variables. Is it on the main road? Yes, no. Does it have a guest room? Yes, no. Does it have a basement? Yes, no. So let us look at these categorical variables now. So we are going to make a box plot to understand how many categories are there. For example, main road versus price, there are 2 categories, yes and no. Guest room, yes and no. All these can be handled. What we are going to do is, it's a short trick. All the yes values, we're going to assign 1. All the no values, we're going to assign 0. And that's as simple as that. So these are all fine, but the problem is here. Semi-furnished, unfurnished, and furnished. We cannot assign 0, 1, 2, because when we do that, 0, 1, 2, we are actually giving priorities or ranks to these categories. Sometimes we don't need that. Yes and no. Is there air conditioning? Okay, 1. Yes, because it's a positive thing. But here, what if somebody is specifically looking for a semi-furnished house? It doesn't make sense to rank these features. So what we are going to do is we are going to use one-hot encoding for that later on. Let's first map these yes, no's to zeros and ones. We'll look at the data once. This is how the data looks like. We'll assign yeses, no's to all the, or we'll assign 0, 1s to all the yes and no's, and we'll look at the data again. See, all the yes and no's are assigned 0 and 1. We're good with that. The problem now here is handling the furnishing status. So we'll use one-hot encoding. What exactly is that? We break that column into 3 different columns, or n number of columns, n number of categories that are there in that column. Let's say here in this case furnished, unfurnished, and semi-furnished. We'll break it into these 3 categories, and we'll assign true, false to those. So how is it going to look like? Let me show you. This is how it's going to look like. So if let's say a house is semi-furnished, obviously if this is true, all the other, both of the other ones are going to be false, because the house can only be in one state at a time, right? So this house is semi-furnished, so all the other 2 are false. If it is unfurnished, then the other 2 are going to be false. Now we can just put this directly in the data and get rid of that column we had already with a string. But the problem here, it's not really a problem, but it's a better thing to do. You can always use 2 fields to get the value of the 3rd field, right? If you know here is a true, you know that the first field is going to be false, and the 3rd one is going to be false too. If you know that, let's say if we omit furnished, let's say we only have semi and unfurnished, if you know that this one is false, this one is true, the other one is going to be false too. So they have a relationship between them. So we don't need all of these columns. We are going to drop one of these as well. We're going to drop furnished because it doesn't give any meaningful context to the model. It's a predictable data. We're going to get rid of that. So we'll drop it, and then we'll print the head again. So we dropped it and concatenated it to the existing data, and this is how it looks like. Furnishing state is still there. Let's get rid of this, and we are only going to have these 2 columns. So this is our final data set. We have price, area, all the quantized numbers like bathrooms, bedrooms, stories. Everything looks good here, and these are also true, false now. So the entire categories have been handled. Let's go ahead and split into train and test. We'll use 70% of the data to train the model and 30% of the data to test it later on. Perfect. Now, normalization. What is normalization? Very quickly, if you look at these values, these are very small values, 0, 1, 1, 0, 0, 0, 1, 0, 1, 2, okay? But then look at the area. Area is also an independent variable that will be used to predict the price of the house later on. This is very big. So this is going to overpower the rest of the columns. We need to shrink it down into a certain range so that, I mean, technically speaking, when we build out the regression equation in the end, it's not really going to have a mathematical implication, but the equation when we build the equation, the area, the parameter for the area is going to be very small, like 0.00056, and for stories is going to be have 578. It's like a very big integer. So we need to take care of that. So we'll just bring all these columns in the range of 0 to 1 so that none of the columns overpower each other. So we'll use min-max scalar to bring it between the range. We do that for train as well as test set, only for the data that is going to be trained, not to the value that is going to get predicted, right? We are not going to touch that. Let's print ahead again, and this is how it looks like. Everything has been bought in the range of 0 to 1, and all the categorical values have been handled. Perfect. Let's look at the correlation coefficient. So what it tells us is if one value increases, how is it dependent on the other value to increase or decrease? So for example, if you look at this minus 0.63, it's a negative value. That means the more probability that the house is semi-furnished, the less probability that it's unfurnished, obviously, because these are categories, you can only have one. So that's how you build the correlation chart, and you try to analyze if there is any redundant relationship between them, so that we can get rid of those values as well. Let us divide it into train and test set and build the linear regression model. So right now we are going to build a linear regression model, and we are going to train it on this data. Perfect. Now let us this y predict values, this y predict variable is going to predict, and it is done already. It's as quick as that. And if we look at the final scores, the R square score is 0.65. So it's usually between 0 and 1. And this is the scale. So if the more it tends to 1, the more perfect the model you have made. And the more it goes closer to 0, it is as good at finding the mean of the rest of the values, because mean defines a trend, right? And then if it can even go negative. So 0.65 is a very good R score for the first iteration. And this is exactly what I want to tell you, that when we build models, the first iteration is going to give you something like 0.65, 0.55, even less than 50%. And that is completely okay, because you need to experiment with the data a lot. You need to try a lot of models before you actually decide on what it is going to look like. So this is how the actual versus the predicted data looks like. These need to be very close to the red line. And with 65% accuracy, it looks good. And if we try to extract the final equation in the end, this is what the equation looks like. The price equals some constant number plus this into area minus this into bedrooms plus this into bathrooms, something. So this is because the price is a very big number, right? And all the other variables were small. So we have like big integers for every column. So this is what I wanted to talk to you about. In the end, it could be a good fit or a bad fit in case if it's an underfit. For example, this model that we just built is an underfit. You can add more features or use more complex models. For example, in this case, we could use polynomial regression or something like that. And in case if there's overfitting, let's say it is taking a lot of waves, then you just add more training data or use simpler models. For example, if there's a linear relationship between the data and you use a polynomial regression model, it's going to take a lot of unnecessary turns. That is all I wanted to share. Thank you so much.